Good afternoon. My name is Frederik Haseke. I'm with the University of Wuppertal and the company Aptiv. And today I will present to you our new paper, What Can Be Seen is What You Get. Structure-Aware Point Cloud Augmentation. Or, as the alternative title goes, augmenting segmentation data is better than annotating 10x more data. And this is a very bold claim. But if you follow along, you will see that we have real proof for this claim. So please join me on this adventure. Let's dive right in.
When we look at segmentation data, for example here the SemanticKITTI dataset, it is clear to see from a first glance that the point distribution, meaning the amount of points for each class, is heavily unbalanced. We have many more points for the classes road and vegetation compared to points in the class of truck or pedestrian. This is also visible when we use the log scale to show the amount of points per class. And here it's even more noticeable that we have way less points for the motorcyclist class compared to, for example, the car class. Additionally, you can see here when we look at the training set of the SemanticKITTI dataset, the trajectories are often looping. So we have sequential data of the same positions again and again and again. So not only is the class set unbalanced, we also look at some things multiple times in the training set without any additional knowledge gained by that. Regarding the first issue of a heavily unbalanced class set, we want to use this scene here and we want to inject more points of various underrepresented classes. In this case, we first have to build a database. Since we need the underrepresented classes, we switch to a completely different scene. And here we simply select the dynamic instances, so cars, pedestrians, motorcycles, and for every single of these instances, we look at the class, for example here, motorcyclist, and second, we count the amount of points and the grade of occlusion. This motorcyclist here, it is not occluded at all. We have a good amount of points, so yes, we will put this into our database. Next up, this car. We have a very good view of the full side and the rear of the car. Therefore, it's a prime example of a good car instance. We also take this into our database. The next car instance, on the other hand, is very occluded by a car in front of it, and we only have a few points of the roof. This is not a good example of a car. We do not want to keep this. The next one is a very good side view, so this is a good example of a car. And we repeat this whole process for every single instance of this frame. So for every car, pedestrian, motorcyclist, we use some very basic heuristics to decide if we want to keep this in our database or not. And of course, we don't just do this for one frame or for two frames. We do this for every single frame in the training dataset. And here I want to mention not the validation dataset, so we never take instances from sequence number 8, on which we validate our methods later on. From all other sequences, we take all the instances, apply our heuristics, and the good ones get into our database. Now we look back into the scene we want to enrich with these instances. There are previous methods out there, some of which simply sample from a database like ours and put in a car here, a car there, the truck over here, and all those instances which we need just at random locations, rotated randomly. But we take a different approach. We do not want to inject them randomly. Our method is, as the name says, structurally aware. We know the structure of the lidar data. To show you what I mean with this, when we look at our lidar frame, you see the clear structure a lidar sensor has. In this case, we use the KITTI dataset, which has a Velodyne lidar with 64 lidar channels. That means these rings you see are 64 laser sending and receiving units, which are rotating around a given axis. So while normally we see this 3D Cartesian point cloud, the lidar actually only sees range measurements. So we have the 64 channels here, and they're rotating around the joint axis. And while it is scanning the whole 360 degree, it is building up a panorama-like image internally. So when we take the 3D Cartesian point cloud and reformulate it as a range image, you see at the bottom here, we're actually much closer to what the lidar originally saw than this 3D point cloud at the top. With the knowledge of the laser module or the laser channel, as well as the angle in the point cloud, we can say for every single point in the range image, which point in the 3D Cartesian point cloud it corresponds to. So therefore, a 3D Cartesian point cloud is actually a 2.5D point cloud in the spherical coordinate views. We take advantage of this property since the 2.5D formulation means for every single pixel in the range image, there is only one 3D point which is corresponding to this position. When we inject, for example, a pedestrian here to the left of the ego vehicle, we use a very simple comparison. If any points in the original scenes are occluded now by this pedestrian or the other way around. For this, we formulate a range image of the scene around us, as you see at the bottom here. And additionally, for the almost empty, except for the pedestrian point cloud we are injecting, we also generate a range image. These two range images now share certain pixel positions, and for every single pixel that the pedestrian is occupying, we can compare pixel per pixel with the range image of the original scene, which ones of these points is closer to the lidar sensor. And once we have this formulation of a pointwise range competition between the injected pedestrian and the original scene, we can ray trace through the full point cloud, and for every single point, we can say this point cannot be recorded by the lidar if this pedestrian is injected here. And we use exactly this property to remove all occluded points from both point clouds. So if the pedestrian is now occluding the house wall behind him, we remove the points. On the other hand, if the pedestrian is behind a pillar, we would remove parts of the pedestrian. With this very simple and straightforward formulation, we can just inject the pedestrian at every single rotation position around the ego vehicle we want. It doesn't matter if there is already something there. When it's occluded, we cannot inject it. When it is occluding, we remove the background. Therefore, we can freely position the pedestrian, or also a bigger object like this truck, all the way around the vehicle and inject these additional instances into our scene. And we can go even further. Why just one pedestrian? Why don't we inject 10? Why don't we inject 100? With this crowd setting, we can actually, when we blend in the point class distribution again of the original scene, we can boost the point count of the pedestrian class so far that it's almost the most prominent class of the scene. But is this really useful? Basically, no. We want the most diverse scene. In this case, when we just inject pedestrians, we have way too many pedestrians. Therefore, we want to inject basically everything that is underrepresented. But how many do we inject? Do we inject 3, 5, 1 of each class, 10 of each class, 100 of each class? The scene can get crowded easily. And you see, even when the point count of all the classes is now basically normalized, our performance will decrease. We've actually tested this, and when we produce crowded scenes like this ones, they are not representative anymore of the validation and later on your application test set. We found a good position is about 3 to 5 instances of various underrepresented classes. You don't need a motorcycle, for example, in every single scene, but you need more of them. They are direly underrepresented. And we provide this. With this very simple injection method, you can just sample the few instances you have of motorcycles and from time to time inject them again in different orientations and positions. These injections provide the solution to the unbalanced class set. But there's still the second issue. When we have sequentially annotated data, we have many point clouds which are very, very similar to the previous ones and the following ones. This is redundant data. Our networks don't really learn much when they see the same scene again and again and again with only slight changes. And even if we compare point clouds from completely different sequences in different parts of the recorded town, we still see very similar patterns. We still have the road going straight ahead with sidewalks left and right, cars parked on the sideways. It all looks basically the same. And here is where our second method kicks in. We take 2 point clouds from randomly sampled locations in the dataset. And while the first one is the one we selected previously, the second one is from a completely different set. And here we use the same method that we used in the injection step, but for the full point cloud. So instead of only taking instances from one point cloud and injecting it into a different point cloud, we thought, why don't we take whole chunks of one point cloud and put it in a different one? And this is exactly what we're doing. But instead of simple chunks, we compare every single point of the given point cloud with every single point of another point cloud. So when we formulate these range images from earlier again for scene number 1 and scene number 2 and overlay them in the orientation we have them facing, we can define for every single point which one is closer to the lidar sensor, and we keep only this one. The one further away is not interesting to us since it's occluded. Quick warning, if you suffer from motion sickness, please look away. As you can see, when we use one point cloud as a static frame and rotate the second one freely around, we can, from only 2 point clouds, create thousands of different subpoint clouds. Depending on the orientation of the second point cloud, different parts of each of the 2 point clouds get injected into the new point cloud. We remove the occluded parts, and what we end up with is a completely morphed view, which is exhibiting parts of each of the 2 parent point clouds, but it's completely different. And this is something which is very, very valuable for our segmentation networks, since when the context changes this much, it cannot rely on priors which it had learned. For example, cars are between a road and a sidewalk. Cars can be anywhere now, but this is not just a mixture. We still keep the structure of the lidar alive. So if we ever see a scene in the real world in which this is the reality, this is exactly how the lidar would capture it. And this is an important distinction, since the structure-aware method we present here will provide data which might look nonsensical to the human user, but it is consistent in the data format. With these 2 methods I've presented, we are not only able to solve the class imbalance, but also increase the diversity of the full dataset. And the best part is, we do not work in the model domain. All our methods are applicable to the raw data input, and therefore we could apply all our augmentation methods to multiple neural networks. In this case, we took 4 open source networks, namely RangeNet, SalsaNext, KPConf, and Cylinder3D. And you can see here in this table, our augmentation methods improved the performance on all 4 of these networks. We did not change anything in the models. We took the training scripts as provided by the authors, and all outperformed the original checkpoints. Additionally, we wanted to test which parts of our augmentation pipeline are important, and do we really need this fusion in which the point clouds look strange. If you look at this table over here, you can see, to our own surprise as well, the fusion method is actually more effective than just the injection method. But in the end, the combination of the 2 methods together provide the best results. And now, to circle back to my first claim in this presentation, I want to show you the performance of the Cylinder3D network in this example with our augmentations and without on reduced datasets. So we took the original SemanticKITTI dataset and we artificially reduced the amount of data we train on. For the baseline, you can easily tell with less data, the network performs worse and worse. And in all the bins with our augmentation methods, it is improving all the time. But most importantly, if you look at the red and green circle, what you see here is that with just 10% of the original data, the Cylinder3D model performs better with our augmentation data than the original model without our augmentations on 10 times as much data. To summarize, our structure-aware point cloud augmentations improve the performance on all models we have tested. Additionally, you can improve your performance even on very small datasets. I hope these methods are relevant to you. If you want to talk about them in more detail, you can reach me under this email address. And lastly, thank you very much for your attention.